Hi dear students, hi, I am Vipin Mishra and I welcome you all in this smart revision series of IMS Academy. So last week we did the revision of power system and you all have enjoyed those lectures. Now in this lecture we are going to just complete the revision of power electronics. So this complete revision of power electronics I have divided into two slots, the part 1 and part 2. So what we will discuss in these lectures. So this is the complete syllabus of power electronics that we have. It consists of 4 chapters: power semiconductor devices, DC to DC converters or choppers, rectifiers and inverters. So we will complete this revision in 2 lectures. Part 1 we will cover power semiconductor devices and DC to DC converter, and tomorrow again we will meet at the same time and we will discuss the rectifiers and inverters. So these 2 lectures will be of total duration of 3 hours. So you will be able to revise the complete subject power electronics, all the formulas, all the important point in these 3 hours. Okay. So let's get started with the first chapter, which is power semiconductor devices. So what are the important topics and what is the weightage of this chapter? So this chapter has a weightage of around 2 to 3 marks. You may get 2 or 3 marks of questions from this particular chapter. Okay. Last year power electronics normally has an average weightage of 11 to 13 marks, but last year it has only given a questions of 6 marks only. So this year it is going to be a subject which will give you more number of marks in the exam. Okay. So be very well prepared with the power electronics, and this series will help you in doing that. So we will first start with maybe power semiconductor devices. What are the important topics? You should know about all the devices and their operations, then switch realization, switching power losses and commutation circuit. You can expect question from any of these topics. Now, so let's get started. So first of all, we will discuss with the switch realization. So constantly there has been question in the GATE exam from this topic, switch realization. So how a particular switch will be realized? So a switch will be realized based upon what voltage it is blocking when the device is in off condition and what current the device is conducting when it is in on condition. So the voltage blocked during the off condition and the current conducted during the on condition. Okay. Now you should also know about the active and passive switches. So what do you mean by passive switches? So just see this particular switch which I am making here. So we have only 2 terminals here. Okay. And here is the voltage applied, and this is how the current will be flowing when the switch is conducting. Do we have any control terminal? No. So if when it comes to passive switches, there is no control terminal present. Okay, there is no control terminal. So their operation is like uncontrolled operation. Okay. So there is no control terminal present, and examples can be diode. So in diode we only have 2 terminals, there is no control terminal. Once you will apply voltage of like polarity, the device will conduct, or if you will apply the voltage of opposite polarity, the device may come into off state. Okay. When it comes to active switches, just see. So we may represent an active switch like this. They have a control terminal as well. This is AB and this is the control terminal. So like that you can see here is the voltage, and when the switch will be on, it will be conducting a current IAB. So whether, first of all, what you will do, you will apply a like polarity so that this device may come into on state, but it will not come into on state until you will apply a control signal that will trigger the device. So active switches, they have a control terminal that will control the operation of the switch. Whether the switch will be in on state or off state, it will be determined by the application of control signal through the control terminal. Examples can be all the switches that you normally study: BJT, MOSFET, IGBT, SCR, GTO, all the switches, they are active switches. Okay. So now minority carrier device and majority carrier device, this is also something that you should know. Question has been asked from this particular topic as well. So what do you mean by minority carrier device? So if a device is a minority carrier device, the conduction will be due to, the conduction is due to both electron and holes. Okay. But when it comes to majority carrier device, the conduction will be only because of either electron or hole, means only one type of charge carrier participate in the conduction. Okay, examples here can be BJT, IGBT, diode, etc. Okay, but examples here are very restricted. For example, MOSFET or sometimes Schottky diode as well. Okay, now why we are discussing this? If both type of charge carriers are participating, that means the on time and off time, it will be very high. So the total time for the switch transition, which comprises of T off and T on, and you know that T off had some recovery time as well. Okay, TRR, reverse recovery time. So what will happen in these type of devices, TRR or T off time will be more, so ultimately T will be more. So what about the switching frequency, which is 1 by T? So if T is more, F will be less. So minority carrier devices, they will be having less switching frequency. They will take more time in their on and off transition. But when it comes to majority carrier devices, what will happen here is this T, which is T on plus T off, and this T off has reverse recovery time as well. So this will be less here because we only have to recover only one type of charge carrier, isn't it? Either electron or hole. So it will take less time. So if this will be less, the total time for on and off transition required will be less. And if this is so, the switching frequency, which is 1 upon T, so if T is less, these type of devices will give you higher switching frequency. Okay, so whenever higher switching frequency applications are there, high frequency applications are there, your choice will be a majority carrier device. For example, MOSFET. So MOSFET is a switch that will give you highest switching frequency operation. Okay, highest switching frequency. So this is the advantage of majority carrier device, and you should know about minority and majority carrier device. You may get an MSQ type of questions out of this. Okay, after that, moving into the next topic, let's discuss all the switches one by one. Okay, so diode. So when it comes to diode, what is the circuit symbol? This is the circuit symbol of diode. Okay, two terminals, anode and cathode, no terminal, control terminal. So this is a passive switch. Diode is a passive switch, and not only a passive switch, if we want to diode is also a minority carrier device because both type of charge carrier participate. Okay, so minority carrier device, and if it is a minority carrier device, its frequency will be very less. So switching frequency up to 1 kilohertz you can use diode. And this is an uncontrolled device because it is a passive switch, so it is an uncontrolled device. Now when it comes to the switch realization, diode can be realized in this manner. Just see, if you want to realize the diode, the switch realization of diode will be like this. It is capable of blocking the negative voltage when it is off, and when it will be on, it will be carrying the positive current. Okay, so the switch realization will be in the second quadrant. Now looking into this, you can comment that it is carrying only current in one direction, so it is a unidirectional device. Okay, it is a unidirectional device. Then it is capable of blocking only one polarity of voltage, so it is unipolar device as well. Okay, so unidirectional, unipolar device. So whatever is regarding the diode you should know is written on this particular page. So this is all about the diode. Okay, now moving towards the next switch, BJT. So what is the circuit symbol? NPN or PNP, two types of BJTs are there, but NPN is more popular. So it has base, it has control terminal, and it has the emitter terminal. Now base is a control terminal here. Okay, so base is basically acting as a control terminal. Whatever voltage, you have to first apply the voltage here. okay. And when you have applied the voltage, the BJT will be turned on only when you will apply a base signal here. You will give base current, okay, until and unless it will be in off state, okay. So since we have a control terminal, so it is what? It is an active device. It is a kind of active device, okay, and both type of charge carrier will participate in conduction. So it is a kind of minority carrier device. It is a minority carrier device, and then if it is a minority carrier device, then F will be restricted. So F, it will only give its you can use BJT up to 10 kilohertz of frequency, okay. Now after that, if it is an active device, means we can control the on and off of BJT, okay. So if it is an active device and we have a control terminal, so it is a fully controlled device, okay. We have full control over its on and off, fully controlled device. You can turn on or you can turn off the device by the application or removal of gate signal, okay. So fully controlled device. Now when it comes to the switch realization, how BJT will be realized? So if you want to realize BJT, just see, we will always apply a positive voltage VC, so it will be blocking the positive voltage, and when you will give the control signal, which is base signal, it will be carrying the current in the positive direction like this. So it will give you a switch realization in the first quadrant, okay. Now again, if you see, it is capable of carrying current in only one direction, so it is a unidirectional device. Unidirectional device. You cannot use this switch where bidirectional current has to be taken care of. Voltage that it is handling is only in one, having one polarity, so it is also unipolar device, okay. So this is all about the BJT that you should know, okay. Unidirectional, unipolar, active device, minority carrier device, frequency up to 10 kilohertz, you can use it, fully controlled device. This is all about the BJT. Then we have MOSFET, a very, very popular switch of power electronics and very important switch. So when it comes to the circuit symbol of MOSFET is something like this. So this is the gate terminal, and then we have drain and source terminal. So this is the drain terminal, this is the source terminal, and we also have an inherent body diode, okay. So we have an inherent body diode present in the MOSFET as well, okay. So again, see, we have third terminal which will give you the full control over the on and off of the switch. So it is active or passive switch, it is an active switch. So MOSFET is an active switch, and if it is an active switch, it will give you fully controlled operation. So it is a fully controlled switch, its on and off is completely controlled by the gate terminal. Again, it is a majority carrier device. It is among the few devices which are majority carrier devices. So it is a majority carrier device. Now since it is a majority carrier device, only one type of charge carrier has to be recovered during the turn off process. So it will give you the switching frequency which is very high. So 100 kilohertz, you can use this switch up to 100 kilohertz or beyond that frequency as well. When it comes to the switch realization, so MOSFET is also a transistor family device. So it will give you a switch realization like a transistor. It will give you a switch realization like a transistor, capable of blocking positive voltage, capable of carrying positive current. But due to this internal body diode which is present here, it will also be capable of carrying the negative current, okay. You will apply voltage like this here. So it will be capable of carrying negative current just because of this body diode. Unless it is a transistor family device, so it will give you a switch realization like a transistor, okay. So now what you can see, what are the characteristic this device is having? It is capable of carrying current of both direction. So it is a bidirectional switch, okay. So you will use that switch where both type of currents need to be carried. So it is a bidirectional device, okay, and it is capable of carrying voltage of only one polarity. So it is a unipolar device. It is a unipolar device, okay. So this is all about the MOSFET. The important factor is a majority carrier device and it carries the highest switching frequency. Okay, it is also a bidirectional device. After MOSFET we have BJT, another transistor family device. Okay, so IGBT. So what is the circuit symbol? Circuit symbol somewhat look like this. It is a mixture of transistor and the MOSFET. So we have a gate terminal and we have a collector and emitter terminal like the transistor. So it is again a 3-terminal device. So it is a kind of active switch and you can control the on and off fully by the gate terminal. So it is what? Active switch and it is fully controlled switch. It will give you fully controlled operation. So fully controlled switch. Then it is a minority carrier device. Okay, it is a minority carrier device. Both type of charge carrier participates, and if it is a minority carrier device, it will give you switching frequency less, which is 50 kilohertz. But this switching frequency is the highest after the MOSFET. Okay, so after the MOSFET, the switch that will give you the highest switching frequency operation is IGBT. Okay, then if you realize the switch realization is somewhat similar to what we have in BJT, because this is also a transistor family device. So what do we have in BJT? BJT was capable of carrying blocking positive voltage and capable of carrying positive current. Okay, so if we see this is a unipolar device. This is a unipolar device and this is also a unidirectional device. Okay, this is unipolar and unidirectional device. So this is all about the IGBT that you should know. Important fact is after MOSFET, this is the switch which can handle the highest switching frequency operation. Okay, now after IGBT we have silicon controlled rectifier, the SCRs. So when it comes to SCR, just see the construction of them. It is a 3-terminal, 4-layer device. Okay, so we have PN layer and there are 3 junctions formed here. Okay, then we have 3 terminals, anode, cathode, and this is the terminal gate. Okay, now it gives you an operation in 3 quadrant. 3 modes. And what are the 3 modes? First one is forward blocking mode. Forward blocking mode. So what will happen in forward blocking mode? The anode is made positive and cathode is made negative with gate left open. Okay, so we will not apply anything on the gate. When we will do like this, what will happen? J1 junction and J3 junction, they will be forward bias, but there is a junction J2 which will be reverse bias and which is blocking the conduction. Okay, so this is what will happen in the forward blocking mode. Then we have the forward conduction mode. Forward conduction mode. So what will happen in forward conduction mode is still anode is positive and cathode is negative, gate is still left open. Okay, so if gate is left open and still we have junction J1 and J3 which are forward bias, but we have junction J2 which is reverse bias. Okay, but we will do one change here, and what is that change? So we will do just one change here, that we will increase the applied anode to cathode voltage greater than a voltage which is called as break over voltage. Okay, if we will do like this, junction J2 which is reverse bias, it will break down. Okay, so as a result what will happen? Junction J2 will break down. Okay, so we are applying very high voltage and breaking the junction J2 down so that the conduction is made possible. But the problem is that device will not be able to capable of carrying coming into forward blocking stage again, means successfully we will not be capable of turning off the device. Okay, it will just lose its forward blocking capability. So this is the problem. Then the third mode that we have is reverse blocking mode. Okay, so device, what is the status of device here? Off. Okay, what is the status of device here? We can turn it on, but this is not at all preferable. This is a false operation because no gate signal is applied, so no control you will get. Then third we have reverse blocking mode. Now in reverse blocking mode, what will happen? Anode is made negative, cathode is made positive, and gate is still left open. Okay, so when you will do that, J1 and J3 they will be for reverse bias, but junction J2 will be forward bias. Okay, so junction J1 and J3 are blocking the current coming from junction J2. So whether there will be any conduction? No. Okay, so no conduction will happen and the device will still be in off state. Okay, so if we draw the character, so this is what will happen here. Okay, this is what will happen here in all the three conduction modes. Now what is the way to turn the device on? So what we will do to turn on the thyristor, or for the proper operation of thyristor, what we will do, we will make the anode positive and cathode to be negative, and we will give the gate, we will make the gate positive with respect to cathode. Okay, so if gate is made positive with respect to cathode, means the gate current is not zero right now, we are giving some positive gate current. When you will do that, the junction J2 will again break down. We are causing the junction J2 to break down, but at a lower voltage now. Okay, there is no possible way of conduction of SCR other than breaking down the junction J2. But earlier, when we are increasing the voltage and breaking it down, it will not be capable of coming into the forward blocking state again. And this is a false operation as well, because you haven't applied any gate signal. But right now, through the application of gate signal, we are still making the junction J2 to break down, but at a lower voltage right now, so it will not lose its forward blocking capability, and it can be able to turn in, it can be able to come into the forward blocking state again. Okay, so this is the thing that we are doing here. So when you will do that, what will happen? The device will now come into the on state. Okay, and the circuit characteristics will be like this. SCR characteristics will be like this. So this is the applied anode to cathode voltage, and this is the anode to cathode current. So earlier what we were doing, we have applied a positive voltage, okay, and this is something called as breakover voltage. So when you have increased the applied voltage greater than the breakover voltage, the device has come into on state. Okay, at that moment you haven't applied any gate current, so gate current was zero here. But right now what we are doing is, you are applying some gate signals. So just see, as the gate current will increase, now let me call this to be IG1, let me call this to be IG2, and let me call this to be IG3. So here IG3 is greater than, IG2 is greater than, IG1 is greater than obviously IG0. Okay, so as you are increasing the gate current magnitude, the breakdown is happening, but right now it is happening at a lower voltage. So you can see the VBO2 is less than, VBO1 is less than VBO0. Okay, so right now you are making the junction J2 to break down, but at a lower voltage right now. And during the reverse blocking mode, which is of no use, this is what will happen. Okay, now during this mode we have two currents. One is the latching current, one is the holding current, and another one is the holding current. Okay, so let me just make it more clear. So another first current that we have is called as the latching current, and the another one that we have is called as the holding current. Okay, and the latching current is approximately equals to 2.4 times the holding current. This is a very important relation. Okay, where the latching current is related to turn on process, and the holding current is related to the turn off process. So latching current is the minimum current that the device should attain in order to perfectly come into the on state. After that, if you will remove the gate signal, the device will still remain in the on state. Holding current is the current that the device should, below which the device should reach in order to come into the off state by applying the negative voltage as well. Okay, so these are the two currents. Now looking into the characteristic, now what you can see here, now what you can see, the important points are, by the application of gate current we can be able to turn on the device, isn't it? So this is an active switch because gate is the control terminal here. So it is an active switch. Without the gate application it cannot be turned on. But whether it is a fully controlled switch, through the application of gate signal we can turn it on, but we cannot turn it off by applying the negative gate signal. So this is a semi-controlled switch, which is very, very important. Okay, this is a semi-controlled switch. We cannot have full control over the on and off process. We have control over the on process, but we do not have a control over the off process. So this is what semi-controlled switch. Okay, and what is happening? Both electron and holes are participating in the conduction. So this is also a minority carrier device. Okay, this is also a minority carrier device. Okay, and if it is a minority carrier device, obviously the switching frequency will be less. Fine. Now how we will realize this particular switch? So if suppose we want to realize the switch, so how you are going to realize the switch? Just see. So switch realization will be like this. If this is my positive voltage, this is my negative voltage, and this is the current. So if you have applied positive voltage, the device has blocked the voltage. If you have applied the negative voltage, the device has blocked that voltage and it is not coming into on state. When you have applied the positive voltage and given the gate current, only then it can come into the on state. So this is what? This is a bipolar device because it can block both type of voltages. Okay, but it is carrying current only in one direction, so it is a unidirectional device. So it is a unidirectional device. Okay, bipolar and unidirectional device. So this is all about the SCR. Now here comes the GTO. So what problem we have encountered in SCR? That we can turn it on by the application of gate pulse, but we can not turn it off by the application of gate pulse, which we will be able to remove here. Okay, so when it comes to now SCRs, the circuit symbol we haven't discussed. This is the circuit symbol of SCR. So this is the gate terminal, this is anode, and this is cathode. Now when it comes to GTO, it will be having a circuit symbol like this, similar to SCR, anode, cathode, and gate terminal we have, but gate has a bidirectional application. By applying the positive gate signal, you can turn the device on, and by applying the negative gate current, you can turn the device off. Okay, so since it is having three terminals, so what we will be the status of device? It is an active switch. Okay, so it is an active switch, and by the application of control terminal, we can turn and turn off, turn on and turn off, both we can do with the device. So it is a fully controlled switch. It is a fully controlled switch. Now minority or majority carrier device, so it is a minority carrier device. It is a minority carrier device. And since it is a minority carrier device, so switching frequency is limited. Okay, when it comes to switch realization, similar to what we have in case of SCR. Okay, similar to what we have in case of SCR. Positive voltage, it will block. Negative voltage, it will block. When you will give the positive gate current, it will conduct. Okay, so what type of device is this? This is a bipolar. This is a bipolar device, and this is also unidirectional device. So bipolar unidirectional device. Okay, this is all about the GTO. Now Triac. So when it comes to Triac, what is the circuit symbol? So the circuit symbol of Triac is like this. Circuit symbol of Triac is something like this. We have empty one terminal, we have empty two terminal, and we have a gate terminal. Okay. So since we have a gate terminal, this is also an active switch. This is an active switch. Okay. Since we have a control terminal, so it is an active switch, and through the gate terminal we can either turn on, we can only turn on the device. Okay. We cannot turn it off. So it is also semi-controlled. Okay. It is a minority carrier device. It is a minority carrier device. Okay. Active switch, semi-controlled switch, minority carrier device, and switching frequency is the lowest among all. Okay. Switching frequency is the lowest among all. Now when it comes to the characteristic of the device, so the characteristic of the device will be like this. Just see, this is the applied positive voltage, negative voltage, positive current and negative current. So it will give you a characteristic like this. Okay. And in the third quadrant also you will get this characteristic. This is when empty one terminal you have kept positive and gate current is positive. This is when empty two terminal is, or empty one terminal, we can talk about empty one terminal. So when empty one terminal, it is negative. Okay. And the gate current that you have given is also negative. Okay. So you can see that this switch is capable of blocking both type of voltage and carrying both type of current. So this is the only switch that will give you 4 quadrant operation. Okay. 4 quadrant operation. So it is bidirectional and bipolar device. This is the only switch that will give you 4 quadrant of switch realization. Okay. So this is all about the switches. You may be asked any question related to them. Now you can see some switches are unidirectional, some switches are bidirectional, some switches are unipolar, some switches are bipolar. If suppose application requires something different, then we have to connect the switches into series or parallel. For example, if suppose we have this switch combination where we have a BJT. Okay, so we have a BJT and we have a series diode connected like this, and this is the A terminal, this is the B terminal, here is the current flowing, and this is how we have applied the voltage. So what will be the switch realization? Diac, please. Jitin, diac you can ignore. Okay, this is not the part of gate syllabus right now. Fine. All these switches that we have discussed is important for you. Diac you can ignore. Diac is very much similar to Triac, but there is no control terminal. Fine. Now just see this particular switch connection. So if we have series combination of switches, so regarding BJT, what is the switch realization? So if we talk about BJT, switch realization will be in first quadrant. Okay. Now if we talk about this diode, so for this diode the switch realization will be in the second quadrant, isn't it? Now just see both of them, they are connected in series. So what do we have in series? So when it comes to a series connection, okay, in general if we talk about the series connection, so in series connection what is the thing that we have? In series connection the current is intersection of the two currents, means in series connection the current is common, isn't it? While the voltage will be union, means voltage will be different. Okay, voltage will be different. So you have to take both the voltages present here and you have to take the common current. So what will be the switch realization of this combination? The switch realization of this combination will be like this. Just see. Both type of voltages we have to take. So we have positive and negative, we will take both voltages. Same current we have to take, so current we have only positive. So just see, BJT is unipolar unidirectional, diode is unipolar unidirectional, but the combination is right now bipolar and unidirectional. So you can use this particular combination in an application that requires to handle both type of voltage but carry current only in one direction. So that's why we do switch, we connect switches in series, okay, and this is all about the series connection of switches. I hope this is clear to you. Now we can also have parallel combination. So if suppose we have parallel combination of switches, so parallel combination of switches, just see, if we have this kind of switch, okay, then what about the BJT? So if we talk about the BJT, the switch realization will be, just see, in the first quadrant you will get the switch realization of BJT. Now just look into this diode. This diode is connected in reverse manner, okay. So for this diode we have this switch realization. If suppose the diode is connected in reverse manner, you will just reverse the switch realization of a normal diode, okay. So just see, in a normal diode what do we have? We will get the operation in the second quadrant, okay, where negative voltage and positive currents are there. But if you have reverse diode, what you will do? Positive voltage and negative current will be the switch realization of this reverse diode, okay. Now they are connected in parallel. So in parallel what happens? In parallel what do we have? When it comes to the current, so current is different in parallel connected element. So current you will be taking by the union, and voltage in parallel remains same. So you will take the intersection of voltages in parallel connection. So just see, out of these what we have to do? We have to choose the common voltage and different current. So what will be the ultimate switch realization? Now that will be, if this is voltage current minus negative voltage negative current. So what we have to do? We have to take the common voltage. What is the common voltage here? Positive, okay. But we have to take both the currents. So we have positive and negative current. We will be taking both the currents, okay. So just see, BJT is unipolar unidirectional, diode is unipolar unidirectional, but the combination has become right now unipolar and bidirectional. So you can use this combination in such an application which requires to handle one type of voltage but two types of current. Those applications will be DC applications or inverter applications, isn't it? So you can use this combination in those applications. So this is how and why we will do the parallel connection of switches. I hope this is clear to you. Then another important topic from where you can expect questions in the GATE exam is the switching characteristics of BJT. So what is this switching characteristics of BJT? Let me draw the switching characteristic, okay. So this is the time evolution, okay, and this will be voltage and current. So just see, initially what will happen? The voltage will be very high, okay. Let me use different colors. So initially what will happen? When you are going to operate any switch, you will be having very high voltage and you will be having very low current, isn't it, or zero current. So initially you will be having very high voltage and you will be having zero current, yes or no? So this is your voltage and this is your current, okay. Now when you will apply base current, base signal to the transistor, what will happen? It will turn into on state. So how the on transition will be happening? The voltage will be coming to a very low value while the current is building up across the device, okay. Then we will call this to be the on time of the device. After that, if suppose you are maintaining that conduction, so this is called as the on process. This is T on process and this is the on state of the device. Device is in on state here. Now let us suppose that you want to turn it off. You will apply negative base current, and when you will apply negative base current, what will happen? Your current will now drop from full value, it will drop to zero value. And if current is dropping, the voltage is building up, okay. So the voltage is building up. So just see, the voltage built up, okay, and then we have the off process. So just see, this is called as T off, where you have initiated the off process and now the device has come into the off state. So this is how the complete transition will happen. Okay, here you have applied positive base current, here you have applied negative base current. Okay, now let me call this voltage to be VCC. Okay, and let me call this maximum current that the device is carrying as ICS. Okay, so this is regarding the voltage and this curve is regarding the current. Okay, so this is the switch realization of BJT. Now what are the losses? If you have to find the energy loss or energy, this is like within the stipulated time period you will integrate the product of current and voltage, or you may also call it instantaneous power. When it is integrated for a certain time period, this will give you energy. Okay, now we have a formula for this process. If suppose we have to calculate the energy during the on process, it will be equals to VCC into ICS upon 6 into T on. If suppose you have to calculate the energy during the off process, this will be equals to same VCC ICS upon 6 into T off. Okay, just see. So this is energy during the on process, this is energy during the off process. Energy during the on state or off state, they are approximated and understood to be 0. Okay, if suppose not, if suppose voltage is not having a 0 value here and current is not having a 0 value here, you will get some energy loss here as well, and you will be calculating in the same manner. Then total energy will be, the total energy will be E during T on plus E during T off. And if suppose you have to calculate the average power dissipated, that will be E upon the total time. Sometimes it is given in terms of switching frequency. So this is everything is written in this page. If suppose you will get a question from this topic, you will be able to just use the formula and calculate the answer. If the numerical is having exactly similar characteristics, you will be using the formula directly. If suppose it is having something different, you will be using these techniques to calculate the energy loss and the power. Okay, so this is regarding the switching characteristics of BJT. I hope this is clear and nobody is having any doubt. Then comes the diode circuits. Okay, so let us discuss diode circuit, and through the diode circuit we are just analyzing the behavior of different loads. Okay, so if suppose we have, first of all, let us suppose, if suppose we have an RC circuit. Okay, then if suppose we have RL circuit, then what are the values of voltage and current? Situation is like this. If suppose we have some DC voltage and through the switch it is connected to a diode, and diode is connecting an RC circuit to the source, which is Vs. Okay, so this is R and this is C. This is the current that we have, and this is the Vc voltage, this is the Vr voltage. This is the situation in which we are in. Okay, so in this condition, what is the voltage? Capacitor voltage. So capacitor voltage is Vc 1 minus e to the power minus t by tau. Okay, where what is tau? Tau is the time constant, which is Rc. If suppose I have to find the current, then current will be Vs over R. This will be Vs. Vs over R e to the power minus t by tau. These are the voltage and currents value in an RC circuit. Now if suppose we have an RL circuit. Okay, so if suppose we have an RL circuit, so the situation is same, but the load is an RL load. So if suppose you have an RL load, okay, like this, where this is VR voltage and this is VL voltage, the time constant now will be L by R. Then in this condition, the current will be equals to Vs over R 1 minus e to the power minus t by tau, and the inductor voltage is given by Vs e to the power minus t by tau. So these are the voltages and current across an RC circuit. These are the current and voltage across an RL circuit. Okay, so these are the important observation. If suppose we have RC load, if we have RL load, this is how the current and voltages will be varying. Okay, now another important load. If suppose we have an LC load, which is very, very important, and you will see this a couple of times in power electronics. So if suppose we have LC circuit, okay, so this is Vs, this is the switch, diode, L and C. This voltage will be VL voltage, this voltage will be VC voltage, and the current flowing is I. So if suppose we have this circuit, what will be the current? So the current in this circuit is basically given by Vs under root C by L sine omega naught T, or sometimes this is also written as IP sine omega naught T. IP is the peak current, Vs under root C by L. Okay, this current is varying sinusoidally. Similarly, if we have to calculate VLT, that will be equals to Vs cos omega naught T. What is omega naught? Omega naught is 1 upon under root LC. Okay. Similarly, if we have to calculate the capacitor voltage, that will be equals to the source voltage minus the inductor voltage. So you will get Vs1 minus cos omega naught T. Okay. So these are the different voltages and current. Now current is following the sine curve, and with the sine you know that at omega t equals to pi the current will become 0, means diode will stop conduction at omega naught t equals to pi. Okay. So if I have to answer the question, the diode conducts for, so the diode conducts for omega naught t equals to pi, or t equals to pi upon omega naught, or we can say pi under root LC. Okay, this is the time for which diode conducts for. Now when diode is off, okay, what is the diode voltage? When diode is on, the diode voltage will be 0. When the diode will be off, there it will not be carrying any current. If there is no current, there is no inductor voltage. Okay, and this will happen after omega naught t equals to pi. So what will be the capacitor voltage? So if you will put omega naught t equals to pi here, cos pi will be minus 1, and you will get 2 Vs voltage. Okay, so the voltage across the diode will be 2 Vs at the end. Okay, not 2 Vs. This will be the capacitor voltage. Okay, so the capacitor voltage will be 2 Vs. Now what is the voltage across diode? So you will get it by applying the KVL, Vs minus Vd minus Vc equals to 0. So from here what you will get as the voltage Vd, so Vd will be Vs minus Vc, so you will get minus of Vs. Of course the voltage will be negative because diode is off right now. So the capacitor voltage after the diode stops conduction is 2 Vs, and the diode voltage when there is no conduction is minus of Vs. That voltage is applied through the capacitor. Okay, is that fine? So this is what will happen in an LC circuit. I hope everything is clear. Then if suppose we have AC circuit supplying to an inductor with the help of a diode. Okay, if we have suppose this situation, this is the output voltage and this is the inductor voltage as well, and this is the input voltage which is equals to Vm sine omega t. So if we have this situation and the current is I naught, okay, so in this situation this current I naught is given by Vm by omega L 1 minus cos omega naught t. Now if we are going to plot this current, what we are going to get, just see, if we are going to plot this current, we are going to get this plot. Okay, here is your pi and here is your 2 pi. So at pi, when you will put pi here in this equation, you will get Vm by 2 omega L. That will be the maximum value of this current. Okay, so I naught max will be Vm by 2 Vm by omega L. Okay, that will be the maximum value of it. Now what you can see here, that current has started conduction at omega t equals to 0 and it becomes 0 at 2 pi. That means if we ask a question that diode conducts for, so the diode conducts for 2 pi radians, okay, or 360 degree. So diode conducts for a duration of 2 pi or 360 radians. Okay, this is for pure L load. For pure R load, if suppose we have pure R load, the conduction duration will be only pi or 180 degree. If suppose we have an RL load, then the conduction duration will be from in between pi to 2 pi, okay, or in between 180 to 360, anywhere in between 180 to 360. Okay, so this is a very important thing that you should know. If we have L load, this is how the characteristic will be. If we have R load, this is how the characteristic will be. If suppose we have RL load, current will end somewhere here and you will call this angle to be beta, the extinction angle. Okay, so this is for L load, this is for RL load, and this curve is for R load. Fine. So if we have suppose AC circuit exciting to a pure inductive load or R load or RL load, everything is being summarized here. So conduction duration of diode you can find from this thing. If suppose we have AC circuit supplying to a capacitor, in that situation what will happen? So this is the capacitor voltage, okay, and this is the input voltage. So when diode is on, what will happen? When diode is on, your capacitor voltage will be equals to the input voltage, and which is Vm sin omega t. Now if we have to find IC, which will be C dVc by dt, so when you will put this value, you will get C Vm omega cos omega naught t. Now you know how the cos curve is varying. So the cos curve varies like this. It will start from certain maximum value and then it will become 0 at pi by 2, isn't it? And after that the current will become 0. So if we talk about the diode conducts for how much duration? So here the diode conducts for 90 degree or pi by 2 radian only. Okay, so if it is a pure L, 2 pi, if it is a pure C load, 90 degree. Okay, so this is regarding the diode circuits that we have. Then let us talk about the current commutation circuits. Okay, diode circuits are discussed. Now let us talk about the current commutation circuits. So this is the current commutation circuit that we have. So what you can see here, let me call this current to be ITM current. Okay, and then we have this current which is IC current, and other current is I naught. Now this IC current is flowing in an LC circuit. So what is this IC current? This IC current is Vs under root C by L sin omega naught t, or you may also call it IP sin omega naught t. And what will be the capacitor voltage at any instant? It will be given by Vs cos omega naught t. We discussed just before this slide, we have discussed all those things. Okay, now just see here, when we have Tm on and Ta off. Okay, so when Tm is on, okay, so when we have Tm on and Ta off, at that time what is happening? Just a second. So when we have Tm on, at that time ITM plus this current IC together, they will become I naught, isn't it? When Tm is on and Ta is off, you have ITM current and you have here the IC current, okay, and together they will constitute the current I naught. Now if suppose we can also write that ITM, that will be equals to I naught minus IC. Now what is the purpose of commutation circuit? The purpose of commutation circuit is to turn off the thyristor Tm. So for Tm to be in off condition, means what should be happening? ITM has to become 0, no current across the thyristor. Then we have to have the condition that I naught equals to IC. Yes or no? So when we will be having this condition that I naught become equals to IC, ITM will become 0, and at that time capacitor must be applying a reverse voltage across this device, and that's why it is off. So what we have here that I naught is equals to IC. Okay. Now I naught is I naught, but IC is IP sine omega naught, and let us suppose this is T dash. The duration at which this is happening is T dash. I am writing is T dash. So what is this omega naught T dash? That will be sine inverse I naught over IP. Okay. And at that time, if we calculate the capacitor voltage, okay, so the capacitor voltage at that time will be acting as a reverse voltage, isn't it? It will be having this polarity and it is acting as a reverse voltage across the thyristor, and we know that how to write the capacitor voltage. This is Vs cos omega naught, and right now the duration is omega naught T dash, which we have calculated from here. Now if we will put this value, we will get Vs cos omega naught T dash is actually sine inverse I naught over IP. Sine inverse I naught over IP. So this is how you will calculate how much voltage capacitor has applied to turn off the switch. Okay. Circuit turn off time is another important thing, and that you will be calculating through C VR upon I naught. Okay. So this is an important formula. These two are the important formulas. Okay. Another important formula is this one. Fine. Now if I ask you what is the peak current across the thyristor, ITM peak. What is the peak current across the thyristor? So thyristor current is basically I naught minus IC. Okay. If suppose there is no IC, I naught will be there, isn't it? If suppose the diode is off, then what will happen? There is no IC current. So ITM will be equals to I naught. When IC comes, ITM carries somewhat less current. So what peak current it has carried is equals to I naught. Okay. And if I ask you what is the ITA peak, what is the peak current that auxiliary thyristor has carried? So auxiliary thyristor is carrying what current? It is carrying the current IC. Just see, IC current will be flowing like this initially when TA is on, isn't it? So this is how this current will be flowing when TA is on. So TA will carry IC current. So what is the peak value of IC current? Is IP. So the peak value across the thyristor, auxiliary thyristor, will be IP. Just see. So all these are the important formulas written in front of you, and you can analyze this anytime. Current commutation circuit will always be given in the problem, and you can analyze everything whenever you want. Okay. So no need to pressurize yourself for remembering the formulas. Now after current commutation, we have voltage commutation. Now what will happen in voltage commutation? Just see. This is the circuit of voltage commutation. Okay. So again, just see, this will be what? ITM current, and we have this current as IC. So when IC will be flowing, it is flowing in this direction, and here we have the I naught current. So right now what is the KVL that we have? KCL we have. So KCL will be ITM, this is equals to I naught plus IC. Okay. Now let me ask you one question. What will be ITM peak? So ITM peak will be I naught and the peak value of IC, which is IP. So what we will be writing here? I naught plus Vs under root C by L. Now that will be my peak current, ITM peak. That will be my peak current here. Okay, ITM peak will be I naught plus Vs under root C by L. Now if I ask you what is the ITA peak? What is ITA peak? So just see, ITA peak. When this thyristor will be on, it will be carrying current like this, isn't it? This is what will be the flow when thyristor TA is on. So can you tell me what current thyristor is carrying right now? It is carrying I naught. Okay. So ITA peak will be equals to I naught. So this is how you will calculate ITA peak current. Fine. So this is how you can just analyze this, and these peak currents are very important. They will be asked in the exam. Okay. Now what is the circuit turn off time? Circuit turn off time will be C, capacitor voltage Vs divided by I naught. Okay. So these three are the important formulas that you should be prepared regarding the voltage commutation. Rest is not important. So these three formulas are important. You will be asked to calculate ITA peak, ITM peak or circuit turn off time regarding the voltage commutation. Okay, I hope this is clear to everyone. So current commutation, voltage commutation is done. Now Fourier series for power electronics. When you will go into the converter circuits, rectifiers, inverters, choppers, every time you have to write the Fourier series for the different converters. So every time remembering the Fourier series expression is a very difficult task. So what I have identified that there are only 3 cases available. If you will identify how to write the Fourier series for those 3 cases, you will be able to write the Fourier series expression for all the converters available in the power electronics. Okay, in which the first case is a perfect square wave. So if you have a perfect square wave like this, the Fourier series expression will be, let me call this output V naught. So Fourier series expression will be summation n equals to 135 to infinite 4, what is the magnitude? Vs. You have to write the magnitude here, 4 Vs upon n pi sine of n omega naught t. That is going to be the Fourier series expression for this. Now just look into this case. Sometimes you may get this case as well. So when you will compare, you are writing Fourier series for this case. What you have done, you have shifted this case towards the right side. Okay. So if we have to write the Fourier series for this, write the Fourier series for this, isn't it? Just by shifting the expression. So what will be the Fourier series here? You may write it n equals to 135 to infinite, the same expression 4 Vs upon n pi, and you will write sine n omega naught t plus alpha or phi n. Let me write phi n. Okay, where phi n is the degree by which you have, or if this is, let us suppose we are writing this alpha. So phi n will be here minus of n alpha. Okay. Just see, this is how you will be writing the Fourier series expression for this case. So perfect square wave, shifted square wave, and we have another case which is called as quasi square wave, which you will see at so many places, in inverters, in semi-converters, everywhere. Okay. So just see, this is a quasi square wave, and what you have to see in this quasi square wave is whether this duration is similar or not. This duration has to be same. If it is not same, you have to shift a little bit. Okay. So if suppose we have this kind of expression for waveform, then what will be the Fourier series expression? This is n equals to 135 to infinite 4, and what is the magnitude? Vs over n pi, and just see, this is theta. So you have to write here cos of n theta, rest everything is same, sine n omega naught t. What you have written here? Sine n omega naught t. So right now you are writing here cos n theta sine omega t or omega naught t. Just write sine n omega t, that will be fine. Okay. So just see, you have added this extra term cos n theta here, which is coming from this angle theta. Okay. So 3 cases: perfect square wave, shifted square wave or quasi square wave. If you have practiced these cases, you will be able to write the Fourier series expression for all the converters waveform available in the power electronics. Fine. So this is about the Fourier series that you should know. Then power calculations. So regarding the power calculations, we have few cases. Okay, so we have few cases. So let me write the first case. Case number 1. And what is that case number 1? When both voltage and current are sinusoidal. When both voltage and current are sinusoidal quantities. For example, we have voltage Vt, which is Vm sine omega t plus theta. Okay. and we have current which is Im sine omega t plus phi. So both are sinusoidal or both are of the same frequency. In that case, the power that you will be calculating, average power, that will be equals to Vm Im by 2 cos of angle between the voltage and the current. In another way you can write it Vm by root 2 Im by root 2 and cos of theta minus phi. Okay, this is how you will be calculating the P average. Okay, Vm by root 2 is also known as the Vrms, IRMS cos theta minus phi. Okay, where cos theta minus phi is also known as the power factor. Okay, so you will get this case, or there is a possibility of getting another case which is very popular in power electronics. In power electronics, voltages and currents will be periodic, but they will not be sinusoidal. Okay, so second case is when Vt and It are periodic but non-sinusoidal. They are periodic but they are not sinusoidal. So if they are periodic but not sinusoidal, then what you will do? So if they are periodic but they are not sinusoidal, means we will be using Fourier series expression. For periodic signal which are non-sinusoidal, we use periodic signal. For example, if we have a square wave, if we have a triangular wave, then what we are doing? We are writing the Fourier series expression, and what Fourier series expression is doing? It is expressing the signal into sine and cosine terms. So situation is like this. We have voltage which is having all the frequency term. When you will write the Fourier series, it will be representing the Fourier corresponding the frequency term present in the signal. Okay, so we have situation like this, and current that we have is also having all the frequency terms. Okay, then what will be the average power? Then average power will be V naught I naught plus half summation n equals to 1 to infinite Vn In cos of theta n minus phi n. Okay, this is going to be the formula. Okay, now if you are going to express this or expand it, you will get something like this: V naught I naught plus half of V1 I1 cos of theta 1 minus phi 1 plus half of V2 I2 cos of theta 2 minus phi 2, and so on. So what you can see, the corresponding frequency term will constitute to the power. Opposite frequency term, they have no interaction. Okay, so just see, this is what you will use for power calculations. Okay, so this is the part 1. I will stop here right now. Okay, this is the part 1 of the revision of power electronics. So now I will stop here, and tomorrow we will meet again in the part 2, and where we will discuss the rest of the chapters available in the power electronics: rectifiers, inverters and the choppers. Okay, and tomorrow the timings will be 3 p.m. Fine. Tomorrow we will meet at 3 p.m. to discuss the rest of the chapters. So guys, if you are really liking the teaching and learning methodologies of IMS GATE Academy, these are the program features. You can join our live online program. We are offering 800 hours of live classes with fantastic contents like theory book, exercise book and GQB. 12 personalized mentorship session will be given to you, so you can strategize your preparation with us. 130 plus online test also we are giving you. Okay, so you can join IMS GATE Academy to get the expert level preparation by calling onto these numbers. And you can also join our Telegram group channel where you will get the PDF of the session and you will get the update regarding the seminar, webinar, career oriented seminar, webinar and government job notification. And we are also conducting a daily quiz here which will help you in your upcoming GATE exam. So I hope you understood what we have discussed in this lecture. Okay, Jiten. So we will meet tomorrow again and we will discuss the further topics. Thank you so much for attending this session.